next speaker is Dr. Andrew Higgins. He is a professor of mechanical engineering at McGill University, Montreal, Canada. He has over 25 years of experience in shockwave experimentation and modeling with applications to advanced aerospace propulsion, defense, and fusion energy. He serves as the managing editor of the international journal Shockwaves. His two recent projects have been on developing hypervelocity launcher and a research collaboration with General Fusion Incorporated. In 2018, on sabbatical, he was a visiting scholar at UC Santa Barbara in the experimental cosmology group working on interstellar flight. So please welcome our speaker.
Thank you for the introduction. I'll just spend maybe one more minute and elaborate on my background a little bit more, since I'm sort of a new face to the TVIW community. So as it's mentioned, my background is all in aerospace engineering, and I've spent the last 20 years of jumping through academic hoops at McGill University, where I work in a lab that does shockwave physics. And as the introduction mentioned, I'm the editor of the journal Shockwaves, and you'll see shockwaves make a couple of appearances in my talk today. Just some of my recent projects that I've been involved with. In the last 10 years, I developed a hypervelocity launcher. It's an implosion-driven, explosive-driven launcher. So this launcher is able to launch projectiles of 10 grams up to velocities of 12 kilometers a second. So I also have a collaboration with a Canadian company, General Fusion, that's located in British Columbia. It's using dynamic compression to try to realize a practical commercial fusion reactor. And I was a principal investigator on a microgravity experiment that flew out of the European Space Agency site in Kiruna, Sweden, about 2 years ago. So I've actually been involved with developing hardware that's been over the Kármán line. But the truth is, the story begins when I was a teenager in the 1980s, and I read this book, Flight of the Dragonfly by Robert L. Forward. And I got to know Robert L. Forward when I was a graduate student in Seattle. So my mentor, Abraham Hertzberg, and Forward were good friends, and he would come on campus once or twice a year, and it was always a highlight of my time there to spend time talking to Robert L. Forward about interstellar flight. And it's something that I've thought about pretty much every day since then. And so I've followed this community quite closely. I've been to the last two prior TVIW meetings. So now that I'm in the golden twilight of my career, I've decided to focus my academic research on interstellar flight. So today is sort of my coming out event to announce that we now have a group at my university, McGill University in Montreal, studying interstellar flight, and I'll call your attention to the word experimental. So the students that I'm working with and myself, we're all dirty fingernails people. We like to do things in the lab, and I'll show you some lab results today. So when the Breakthrough Starshot Initiative was announced in 2016, I think they did a really exemplary job in identifying all the problems that need to be solved to realize interstellar flight. And so my students and I spent time studying this list and thinking about things that were well matched to our skill set as mechanical and aerospace engineers. So what we've been focusing on is looking at the structural integrity of the light sail under very intense dynamic loading. That would be the laser. And then we've been looking at the interstellar dust grain and some of the interstellar media impact events. So I'll talk about a little bit about material stability today. The paper that I'm submitting to accompany this talk is looking at how we might mitigate the dust grain impact event. And we're also looking at some more near-term applications of directed energy propulsion, laser thermal propulsion, which I'll talk about Wednesday at the NASA workshop. So let me talk a bit about looking at the sail first. So I think there's concern if you take a very thin, probably submicron light sail and accelerate it at tens of thousands of Gs so that you can do the acceleration quickly in the near field of an Earth-based laser. Is the sail going to look like this, or under the influence of the various perturbations on the beam due to going through the atmosphere, or maybe imperfections in the sail and how it's deployed? Is it going to look like this, or is it going to look like this? So this is a concern I think a lot of people are now recognizing. There's been previously some excellent work done on the stability of the sail, assuming the sail is rigid body dynamics. And there's been a few preliminary studies that look at the deformation of the sail
There's a study that Bryce Casenti and Greg Matloff did in the 1990s looking at the static shape of a sail under radiation pressure. And at the last TVIW, there was a finite element study done. And so we're starting now to think about this question, what if the sail isn't rigid? What if you introduce a sinusoidal perturbation into the shape of the sail? Is that perturbation going to grow or dampen out? So this is a difficult problem to study experimentally in the lab. If you look at the fluxes that Philip Lubin's group proposed of 100 gigawatts per square meter, or in the cost-optimized design that Kevin Parkin published, maybe closer to 10 gigawatts per square meter, these are very difficult fluxes to achieve in the lab. But if you take that laser flux and bounce those photons, assuming perfect reflectivity, that translates into a pressure, in the case of 100 gigawatts, of only about 670 pascals of pressure, which is really nothing. That's actually very easy to realize in the lab using gas dynamic techniques. In fact, these pressures are sort of at the lower end of what we can do in the lab. They're actually difficult to get gas dynamic loading this low. So what we're going to propose to do is use a gas dynamic method to simulate this. We're also doing finite element models of the real case, the radiation pressure. And I'll quickly run through this. I think you understand the concept of finite elements. We break the sail up into pieces, modeling the stiffness as torsional springs. And then we impose radiation pressure here on the underside of the sail. And you can see if it doesn't have sufficient bending stiffness, the sail does this. It goes unstable and develops peaks and troughs. But to look at this experimentally, since we don't have the 100 gigawatt laser, we're going to use a shock tube facility. So a shock tube is essentially taking a high pressure section of gas, popping a diaphragm, and letting that high pressure section expand into a lower pressure section and pushing a shock in front of it. And this gives you very well quantified loading. In fact, the pressure transducers that you buy are typically calibrated using shock tubes like this, because you can, if you measure the shock velocity, you can know the loading usually to within 1%. It's very, very precise. So what we're going to do is build a shock tube. We've done that. We're going to dynamically load a light sail, and we're going to see what happens to it. And initially, when you break the diaphragm, you transmit a shock. The shock reflects off the sail. It begins to accelerate. The shock diffracts around the sail, and then eventually it transitions to an aerodynamic regime where it's sort of dragged along by the gas. And we can model each one of these from first principles. It's relatively straightforward gas dynamics. And then when we do these experiments in the lab, we have some high-speed cameras, which are pretty common these days, but we also have a unique capability called photonic Doppler velocimetry. This is a technology developed at Lawrence Livermore about 10 years ago. Essentially, you take a laser, in this case, a fiber laser. In fact, it's the same fiber lasers that Philip Lubin's group uses in their work. And we bounce it off the front of the sail, take the reflected light, and blend that light back with another beam of the same laser and pick up the beat frequency when you blend those two light beams together. One of them has been Doppler shifted. The other one, the original beam, hasn't. And if you have a really fast oscilloscope, you have a 20 gigahertz bandwidth scope, you can pick up those beats, and you can convert that into a measurement of velocity. Essentially, you slide a Fourier transform along the window, and you can see this. So this is a waterfall plot. Essentially, it's a sliding FFT that shows at time 0, the shock hits the sail. It accelerates under the shock loading very quickly. This is an acceleration of tens of thousands of Gs. And then when it transitions to the aerodynamic regime, the acceleration drops down. So this is a high-speed video of what this looks like. In this case, we were just using a thin steel 25 micron thick disc. This is much thicker than a real light sail would be, but we just turn up the shock tube driving pressure so that the accelerations are comparable. In fact, most of the sails I'm going to show you today are quite thin. So we can also play with materials that might be of interest for light sails. So one material that's been discussed by the UCSB group is using Gorilla Glass. So this is a sample of Gorilla Glass mounted in the shock tube on the left. This purple device is just a holder for it. And I'll play you a video sort of in real time. Here's where the test where the audio is going to work or not. Let's see if we can hear this. Yep. The light sail's inside. And on this test, we actually left the end of the shock tube open. I don't normally recommend leaving your shock tube open like that. You see an O-ring came loose there. So did the Gorilla Glass survive or not? What do you think? Anyone want to guess? Yes? Anybody say no? Oh, no? Okay, so 1-to-1. So let's play the high-speed video. This is at 30,000 frames a second, the same experiment. There's the Gorilla Glass, and it's intact. In fact, if you walk around the lab afterwards, you can often find it laying on the floor. Okay, so this is a piece of Gorilla Glass that's been accelerated, in this case, at 17,000 Gs and stayed intact. So if you ever hear any skepticism, can we take a thin dielectric sail made out of glass, accelerated at tens of thousands of Gs, you can show them this result to say it's feasible. So we can also perturb the loading. So I was talking about perturbations of the drive laser because of transit through the atmosphere. We can put in obstacles into the shock tube to perturb the loading. This is a case where we're loading 4-micron thick aluminized mylar. This is what is representative of what's used on solar sails. Here we're accelerating much greater. This is almost 400,000 Gs of acceleration because we really want to excite some instability in the sail. Here's a side-on view, and you can see it slamming into those laser collimators that are used for our photonic Doppler velocimetry system. So how do we interpret these results? We are doing finite element modeling, but it's interesting that I think there's a connection between this problem and a well-studied analytic problem called Rayleigh-Taylor instability. So this shows up in everything from inertial confinement fusion to astrophysics. It's essentially the problem of if you try to put water on top of oil. Statically, there's no problem doing that. It's in static equilibrium, but we know that if you try and do that, float water on top of oil, it goes unstable and the lighter oil bubbles through. Well, the analogy here is that you have a lighter fluid pushing into a denser fluid, and this is unstable. Okay, and there's a well-developed analytic theory that predicts exactly what wavelengths are going to be the dominant wavelengths that grow. And lately, this theory has been extended by people working in the inertial confinement fusion theory to look at thin elastic membranes. And so we're intrigued, and we're doing tests now to see if this theory can actually predict when we see instability or not in these membranes. So this is a case where we've actually mounted the membrane on a porous open mesh to impose a sinusoidal shape on it so we can see the growth rate of different instabilities that we impose on the sail. And the measurements on the right are from the photonic Doppler velocimetry, showing over the first 100 microseconds or so, you can see a dramatic growth in the amplitude of this sine wave that we had imposed on the sail. In this case, we're actually using an elastic sail. It's actually latex. And I'll show you what a movie of this. This is what happens if you accelerate latex at 120,000 Gs of acceleration. Okay, so I'm going to move on to talk about the title of the talk, which is Strategies for Mitigating the Dust Grain Impact Problem. So this is, I think, a particular concern during the acceleration phase when the laser is on. So as Sasha Cohen mentioned in his talk, when we're coasting through interstellar space, we can fly edge on to try to minimize our capture cross-section. But during the acceleration phase, you have to fly face on. And the interplanetary medium is several orders of magnitude greater in its density, mass density than the interstellar media. And it's about 50-50 grains versus ions. So you can do the numbers on this, and you're going to be, if you take about 1/10 of an AU, which is the distance over which you're going to accelerate, and calculate how many dust grains there are and collapse those down onto the surface of the sail, then each square centimeter of the sail is going to look like this. It's going to have maybe 10 or 20 impacts per square centimeter. Essentially, every 4 or 5 millimeters, you're going to see an impact of a dust grain. What happens when those grains impact? Well, this is, I would just simply point you to this paper by Rich London and Jim Early. So Jim Early is here in the audience. This is probably the best idea anyone has as to what happens when these dust grains impact. This is something we cannot simulate in the lab. So this is, my opinion, one of the big unknowns about interstellar flight. But this paper is certainly, I would encourage everyone to study this paper. It's sort of the best understanding we have of the physics of what happens when a macroscopic object like a dust grain hits a sail. So just in a nutshell, the idea in their paper is that the grain will pass through, but it will have transferred some of its energy to the sail and some of the sail energy to the grain, and it basically undergoes a plasma explosion and feeds most of its energy back to the sail in the form of radiation, which will melt an area a little bit larger than the size of the grain. But there's a lot of, I think Rich London, Jim Early would say there's still a lot of work left to be done on this problem. Well, what happens then? Now you have a damaged area of the sail, and as we've mentioned several times today, the key is having low absorptivity of the sail. It's not that important the sail be perfectly reflective. In fact, it probably won't be, but it cannot absorb even a fraction of a percent of that 100 gigawatt laser flux. If you damage it, you will start to absorb radiation, and that radiation will probably damage the sail further. Okay? And this is something that's well studied in fiber optics. It's called fiber fuze. You can actually have a wave that propagates up the fiber. Some people here have experienced fiber fuze. It moves about a meter a second. And if that were to propagate across your sail, that would be bad. And on a really bad day, you might experience something called laser-supported detonation. This has a very unfortunate acronym, LSD, where you drive a shock wave out. The shock wave would damage the sail. That damage would then couple more of the laser flux, and within maybe a millisecond, your entire sail would just be vaporized. Okay, that would be a very bad day. So one idea that has crossed a lot of people's mind, I've thought about this, if you have to build a 100 gigawatt laser, can you use the laser to clear out the dust before you launch the sail? And the answer is you can't. If you try to spread the laser out big enough to irradiate the total volume of all the possible grains and all the possible orbits of different inclinations and eccentricities and so on, it's just too diffuse. And if you try to sweep the laser out, you can't vaporize grains fast enough to prevent them from coming back into the path. So there's no way you can clear the way. If you had perfect knowledge of every orbit of every dust grain, maybe you could do it, but we don't have that. We don't have that kind of knowledge. But perhaps you can use the laser during the acceleration process to do this. So this is something that my students and I have been doing some calculations on. We start with a Gaussian beam profile and then think about what happens as the dust grain from the reference frame of the sail approaches that Gaussian profile. So the point here is that the sail is likely going to be partially, in fact, largely transparent. And this was pointed out by Jeff Landis back in the 1980s, that if you have a dielectric sail, you can make it highly reflected by adding up successive bilayers of high and low index of refraction glass, essentially, or other dielectrics. But as you add those additional layers, you're also adding mass. And you're increasing the mass faster than you're increasing the reflectivity of the sail. So you actually are better off making your sail just 1/4 lambda thick. Or in fact, as Kevin Parkin showed in a paper he published last year, maybe you want to go even thinner. In fact, he showed that if you're trying to optimize for acceleration, the optimal thickness of the sail is only about 1/7 of the lambda of the laser light in the sail. Okay, that means the sail may be as thin as 100 nanometers, and it would let probably more than 50% of the laser flux through it. So we can basically take that laser flux, 100 gigawatts, and say if we're passing, 50 or 70 gigawatts through the sail, what happens is the grains come in and approach the sail. So this is a calculation which we've done where you basically start out with a grain way out, maybe 100,000 kilometers, and you do the calculation in the reference frame of the sail so these grains are approaching, and you solve the energy balance. You basically integrate the differential equations describing the flux onto the sail, the emission of radiation from the flux of the laser onto the grain, the emission from the grain. And if a 1 micron grain has 100% absorptivity, you will actually vaporize the grain well before it gets to the sail, maybe 50,000 kilometers out. If the grain only absorbs 10% of the laser flux, then the grains get closer to within 10,000 kilometers. If they absorb 1%, they can come within a few thousand kilometers and they get vaporized. But if the absorptivity is only a fraction of a percent, you can't vaporize the grain in time, it will hit the sail. So this is the big unknown, what the absorptivity of these grains are. If there's a grain that's a perfect, sapphire out there, a perfect sphere, and it's in the Mie scattering regime, well, then we have a problem because the absorptivity is just too low. It will hit the sail. Fortunately, the grains that we know about in the interplanetary media tend to be these kind of flockated fractal structures that have relatively high absorptivity. So there's hope that we might be able to vaporize the grains before they get to the sail. But what if we don't? So I think this is what I call the Dr. Strangelove scenario. The bomber always gets through, right? So you have to worry about that one dust grain that's always going to get through your laser and strike the sail. So now you have to worry about this phenomena of fiber fuse. You have a local area of damage, and this thermal wave is going to propagate out. So there's quite a literature on this. There's a whole book on fiber fuse. And if you read this, there's sort of two strategies how you can stop the fiber fuse from propagating up the fiber. One strategy is you defocus the laser flux. You expand the fiber, lower the flux down so it can't feed in enough energy to keep supporting that wave. The other approach is you narrow the fiber, take away the coating, and make the thread so thin that the losses are such that the wave can no longer propagate through the fiber. So in my paper, I toy with ideas how we could adopt these strategies to make a fault-tolerant light sail. So here I'm showing a segmented sail. This is not graphene, but like in Sasha Cohen's talk, he had a hexagonal spacecraft, so I decided to make a hexagonal sail. And so these edges between the hexagonal segments could be perhaps highly reflective dielectric mirrors. So again, as Kevin Parkin showed, you wouldn't want a highly reflective dielectric multi-layer mirror for acceleration purposes, but maybe we could incorporate strips of these into the sail. They would tend to lag behind because they don't generate as much force, or they don't generate as much force per aerial mass, so they're going to lag behind. And then the light sail would be attached to the back of these. So the flux of the laser is coming from the bottom. Here's the main light sail, comes down and attaches at these boundaries to this highly reflective mirror, and then the next segment of light sail picks up off of that. Now you have a dust grain coming from the front. It hits the sail, causes damage. You have a fiber fuse, or on a bad day, one of these LSD waves propagating across the sail. But when it gets into the shadow of this highly reflective mirror, its propagation would be arrested. You basically have stopped it from propagating to the next segment. The other approach that I said is used is to make a very, very thin thread that connects the elements together, so that if you get hit, and again you have one of these waves propagating out, when it gets to one of these thin threads, it can't propagate across. It can't jump from one segment to the next. And in the paper, I did a few kind of preliminary calculations of what kind of gap you would need. In my day job, I work a lot with energetic materials, which is a euphemism for high explosives. And there's a concept called sympathetic detonation. Okay, how far apart do you have to store your high explosives so if one goes off, it doesn't set off the next one? And there's actually theory and guidelines for these things. So in the paper, I kind of do an estimate of what that gap would need to be. If it's just a thermal wave, probably a gap of only microns is enough to stop the wave from going. But if you have one of these laser-supported detonation waves, then you would need a very, very large gap, because there would be fragments launched from one damaged sail to the next. And that would be, again, a really bad day. I'll talk just briefly now about the coasting phase. And I don't have much to add beyond the really excellent talk that Sasha just gave. I think there's been an idea that's been explored in the interstellar flight community for quite a while of possibly using magnetic fields to deflect the incoming charged particles. I think maybe the earliest I've seen is Ian Crawford in the 70s talked about this. I haven't gone back further than that, but certainly since the 70s this was discussed. Let's have a big superconducting coil, generate a large magnetic field, and try to deflect particles. This is even being studied now to protect more conventional spacecraft from cosmic rays and so on. This is being thought about. If you have a habitat or something in space, you need to protect your crew from cosmic rays. Maybe you could put a large superconducting coil around it and deflect fragments. Cosmic rays and fundamental particles. But there's an idea that I've come across in the particle accelerator community that I haven't seen discussed in the interstellar flight community. So I want to make clear I have no knowledge about this topic other than the fact that I'm a guy with the library card, okay? So I can go and read papers on this. And that is a concept called crystal channeling. Okay, this sounds like something that a former governor of California would talk about, right? Crystal channeling. And the idea is this, is if you have layers or crystalline layers of, in this case, silicon and germanium silicate alloy, and you curve or bend those layers, and you have a collimated beam of ions coming in, you can actually sort of bounce those ions back and forth between these channels and deflect them. And you can do this with much greater efficiency than you can with magnetic fields. Okay. And again, there's books written on this. Most of this work was done in Russia. And the formula for bending a particle's trajectory using a magnetic field, this is the Larmor radius or the gyro radius. Most people know this formula. This is the radius of curvature. It's just the velocity divided by the charge to mass ratio in the magnetic field. And on the right, I'm showing the formula for doing these crystal channeling in bent crystalline bilayers. Okay. I think the most realistic magnetic field we could probably make on a interstellar craft would be about 10 Tesla, right? That's what the LHC has. That's what an advanced MRI machine has. And so a proton coming in at 20% the speed of light is 19 MeV. You can deflect that with a radius of curvature of about 6 centimeters. You can turn it through 90 degrees. Okay. If you use this crystal channeling approach and you use silicon crystals, then the electric field strength between the two crystal layers is of the order of 10 to the 12 volts per meter. You can actually deflect a charged particle with a radius of curvature as small as 70 micron. Okay. In other words, these curved crystal channels are able to deflect a particle with the equivalent of thousands or tens of thousands of Tesla of magnetic field strength. So I think this is an interesting possibility. I haven't seen anybody in the interstellar flight community talk about it. And I think it could even be a way to possibly protect against the grains that are going to come. So this is fundamental particles, but perhaps it could also be used for the grains. So what I have in mind here is something like a Whipple Bumper, which is the kind of shielding we use against micrometeorites, orbiter debris, that has a standoff distance from the sail. Now, like what Cohen was talking about, we're flying edge-on through the interstellar media. A dust grain comes along and hits this standoff shield and gets converted into a plasma, like in Jim Early's paper. And now you have this cloud of charged ions coming towards you. And then you feed that into the leading edge of the actual sail or spacecraft, which is made up of these curved crystalline bilayers, and just deflect them out. And again, you can do this over a very short distance, tens of microns, and then the rest of your spacecraft would be shielded. So to conclude, talking about the earlier part of the talk about sail material stability, we've constructed a facility at McGill University to look at this experimentally, and this facility can be used to look at candidate light sail materials. If a new photonic material is developed and you want to see how it survives under tens of thousands of G's of acceleration, this is what the facility could be used for. Turning to the dust grain problem, we have preliminary calculations suggesting that dust grains may actually be able to be vaporized by the drive laser with the light that's transmitted through the sail, because again, the sail is likely to be only partially reflective. Experience by looking at the fiber fuse phenomena suggests that we could possibly arrest the propagation of one of these waves of thermal damage propagating across the sail. This is during the acceleration phase when the laser is on. And this concept of crystal channeling may provide a means to deflect primary, secondary ions that are encountered in the cruise phase when we're going through the interstellar media. So with that, I'll stop.
I noticed when you were talking about using the shock tubes to simulate the laser acceleration, the shock tube is an instantaneous acceleration just like the laser would, but the laser continues hitting that sail for tens of seconds.
Correct. That's why my shock tube won't get us to the stars. Okay, I can create the exact accelerations that the laser would, but it only lasts for about 100 microseconds. But that is enough time to see if it's developing instability or not. So
that's what I was asking. Is there any way to simulate the effect over time to see if the instability might develop gradually?
I mean, we can dial back the shock tube, but the problem then is the instability is going to grow so slowly that it will run out the end of the test section before we can see what happens or not. But we can. I mean, there's no reason why the laser needs to be turned on instantaneously. I think it might be a good idea to kind of ramp up the laser and more gently accelerate things. So this is something I have some experience with my earlier work on hypervelocity launchers. You're better off, gently ramping up acceleration, and it's actually really how you apply acceleration that's the limit. So if you were impressed that we could accelerate Gorilla Glass at 20,000 Gs and not break it, I think we can actually go much, much further. So that very first movie I showed of a little pellet hitting a plate, that little pellet was accelerated at tens of millions of Gs and didn't break. And you can do that if you apply the acceleration prudently, okay? If you slowly ramp it up. And actually, most of the damage that's done is actually when you release the drive. So it's actually when things are under compression that you release that where damage is. So things like glass have incredible strength under compression. It's when you release them, when they go into tension, is usually where damage occurs. Yeah. But we can experiment that. So there's gas dynamically, we can do that. We could actually hit these samples with a ramp compression rather than a shock loading. So we can explore these kind of loadings as well experimentally.
If you want to do some experimental experiments on the dust impacts, you can get a hole someplace which has a picosecond laser. Then you can basically set the conditions for what it looks like after the grain is passed and watch the evolution of the hole afterwards, because basically it's the same time scale. And then the other point being is that your damage during acceleration is a very interesting regime, because at the lower velocities, you actually expect more damage rather than...
Right, from your analysis, yeah. Yeah, I mean, I think it's an excellent suggestion, and several people have made this, that to study the dust grain problem, you're really sort of in the same regime as sort of laser inertial confinement fusion. In fact, you don't even need as big a laser as NIF. You can probably 1 joule, right, would be about the right energy? Right, yeah. So, I mean, about a 1 micron grain going at 20% the speed of light, that's about 1 joule of energy. So a 1 joule laser would be about right. The only caveat I would say is that the post-impact event probably is the same, a 1 joule laser versus a 1 joule, grain. But the actual impact event itself with a grain is a regime of physics that there could be some surprises for us. And I'd encourage everyone to look at the work of a gentleman who you may know of is Young Bae, who has the record for being the only person ever in the lab demonstrate something actually being accelerated by photon pressure. He did some work at Brookhaven in the late 80s and early 90s, looking at impacts in the 100-kilometer a second range. So there was a while in the late 80s where a researcher named Powell thought they actually might have attained fusion by impacting frozen dust grains at velocities of about 100 kilometers a second. This was not cold fusion. This actually was a little bit, I think, before cold fusion, or around the same time. It was, 89, I think, right? And so Young Bae was brought in to look at the analysis of this, and his conclusion is that when you have a macroscopic object, not talking about fundamental particles, not protons, not ions, but a macroscopic object impacting at hundreds of kilometers a second, and you're into the hundreds and thousands of terapascals of pressure, you may achieve states of matter that have never been experimentally looked at before. You may actually have quantum excited states that when they relax, are going to do it via a mechanism of decay superradiance, okay, and that you get a lot of the energy comes out in the form of really energetic X-rays and so on. So I'm not an expert on this, and this is rather speculative, but I would encourage people to look at this because it's something that we can't really do in the lab. So I have a paper in JBIS on this, that there's really no way to accelerate a little 1 micron grain up to 10,000 kilometers a second on Earth. Okay, if we could do that, there'd be a lot of interesting applications, fusion among others. But that's just something we can't currently do. But this is something that will happen in interstellar flight. And I think it's probably the biggest known unknown in interstellar flight. It's something that we know is going to happen, but we don't know the physics of these events.
I'm trying to reconcile the difference between the high G's and the low pressure. So the pressure is just like a kilopascal, which if you look up the ISO for condoms, that's the burst rate for pressure for condoms. So, I mean, these are kind of common kind of pressures. So why we talk about big G's? Is there really some way to understand this difference?
Take a 1 micron layer of anything and apply a kilopascal to it, and it will accelerate at hundreds of thousands of Gs. And if you can keep that up for 3 minutes, you'll be going 20% the speed of light. Okay.
Water that's just 10 centimeters high,
Yeah.
and you get a pressure of
Yes.
kilopascal.
Yeah, and if you could keep that,
So-
the hydrostatic pressure of that
Right,
water
yeah.
acting on a 1 micron thick film for 3 minutes, you will be going 20% the speed of light. Okay, it's F equals ma. Just take out a piece of paper and pencil and do this. So, I mean, this is all of us had. Anyone who's working
Right,
this
yeah, I
problem
understand.
takes a while to reconcile this. I mean, if you visit Philip Lubin, he always shows us to visitors is he has a way to simulate the loading on his proposed light sail. He uses a CPAP machine. Okay, these machines that are designed to give a very slight positive pressure in your airway, so you sleep well at night. Those, apply hundreds of pascals of pressure, but that's actually the pressure of 100 gigawatts of laser flux acting on a reflective sail, and that's all you need. If the sail is very, very thin, submicron, after 3 minutes of that pressure, you will be going 20% the speed of light. It's just my shock tube and your water column can't keep up with the sail. They'll outrun the gas on my shock tube after it's expanded to about twice its initial sound speed. For helium, I can probably push those sails up to about 2 kilometers a second, 2,000 meters a second, and that's it. My gas just can't keep up anymore. But photons can. Okay, they can keep pushing on that sail for 3 minutes, and that's all you need. But I think all of us have taken a while to process that because it's very counterintuitive that a few hundred pascals of pressure is all you need.
Doesn't your semi-transparent sail that allows enough light through to vaporize particles and so on? I mean, doesn't that destroy your acceleration considerably? I would think
It lowers your acceleration. It lowers your
Well,
acceleration.
that's
But the point is, by shaving the sail thinner and thinner and making it more transparent, you're lowering the pressure of the photons, but you're lowering the mass more, so the acceleration goes up. So this is what Jeff Landis and Kevin Parkin pointed out: is that if you optimize for acceleration, you would want a sail that lets maybe 70% of the radiation through, because that gives you the greatest acceleration. It's again a little counterintuitive, but
yeah, you just made your lasers bigger. That's for sure.
yeah, it puts a greater burden on your laser. But if you want to accelerate quickly, and the key is to accelerate quickly so we can do the acceleration in the near field of the laser.
Sure.
Okay, if you want a higher reflective sail, that's fine, but it's going to accelerate more slowly, and now you need to build a bigger optical element to push it out further.
Thank you.
On your crystal channeling, I happen to have been the deputy spokesperson for that experiment at Fermilab.
Okay, so you're going to tell us why it won't work.
Because you need tens of microradians of accuracy to actually hit the lattice with a low enough angle that you get a oscillatory motion within the lattice.
Okay.
You can't even get as we just discussed
Right,
before your talk,
after the
you
last
can't even
talk.
get a milliradian, let alone tens of microradians.
Okay, well, that's the problem we have to solve then. Yeah, thank you. It's valuable input.